think he does. It's in some of the calculations. He doesn't look like at the hydroxide if it's an acid, or if it's a base, he doesn't look for the hydronium. But these are all mixtures of acids, mixtures of bases. So we start off with the strongest acid and work down, or we start off with the strongest base and work down. And then he looks at the strongest acid plus strongest base. Very dilute solutions, etc. Yeah, buffer in blood is very important. So this is an interesting example of it. I really didn't use millimoles, just a preference. But anyway, those are the types of things we looked at. We're going to move on, though, to chapter 18. Chapter 18 is going to be the last of these ice chapters. And so we're just doing more ice calculations. Except we're going to use one new technique for solving multiple equilibria, which we'll discuss here. But the equilibria we're looking at is solubility equilibria. This is for precipitation and dissolution. So what's going to dictate the precipitation dissolution equilibria is KSP. SP stands for solubility product. It's a solubility product constant. It's always written in the same form. But we have the same types of things, equilibrium, common ion. We talk about the limitations here. Limitations would be, we've already discussed some of the limitations with activities, if the concentrations get too high. We have ion pairing type interactions. So there's more of that discussed here. In 18.5, criteria for precipitation. So we're looking at precipitation and dissolution, and how much precipitates. 100%, 99%, 90%, etc. We look at fractional precipitation. Fractional precipitation is used to separate ions. Like we already did a fractional precipitation. The fractional precipitation that we did was we precipitated out the +3 hydroxides and left the +2 hydroxides in solution. So we precipitated out the aluminum, the chromium, and the iron as +3, but left the magnesium, zinc, and others is +2. We're going to look at the calculations involved there. I told you that we have to keep the pH at a certain level. Well, we're going to calculate at what level that pH has to be to prevent the +2s from precipitating. So we can actually revisit that thing we did in qualitative analysis and calculate at what pH we should not exceed to prevent the +2s from precipitating. That's 18.7 solubility in pH. 18.8 equilibria involving complex ions. Complex ions are complexes like the amine complexes, etc. Those tend to be very stable. And so we'll look at KF. I don't know why they didn't write KF here. And so there are two main ones that we're looking at. KSP, the solubility product, and KF. F stands for formation of complexes. And the formation of the complexes is just forward thinking. It's normal. But the KSP is backwards because we're not looking at precipitation. We're looking at dissolution, dissolving precipitates. Okay. Anyway, they have these things. This is precipitation. There's lots of different ways we try to form crystals. One of them is by evaporation of the water. But if you evaporate all the water, then the impurities can also crystallize out. And so we try to leave a little bit of water left with our crystals so that we can wash the crystals and then get rid of the impurities. However, our crystals, if we were to wash them, we'd probably have to wash them with ethanol, 95% ethanol, to prevent them from dissolving again. But even using 95% ethanol will take some of the sharp edges off the crystals because dissolve. So, first thing we're going to look at is the KSP, solubility product. The solubility product is just the dissolution reaction. We call this dissolution. So the forward reaction is dissolution. The reverse reaction is precipitation. And there's an equilibrium here. And so this equilibrium we describe as, here, let me just copy this. Is the equilibrium between the precipitate and its saturated solution. So when I look at this equilibrium here, if we have this at the bottom of a beaker, let's say we have some solid calcium sulfate here at the bottom. Calcium sulfate's white. I'll make it green here. So this is solid calcium sulfate here. And then in the water, we're going to have a saturated solution of calcium ions and sulfate ions. This would be calcium sulfate solid. Once we hit this equilibrium, then what we say is the dissolution rate, this forward arrow's dissolution, is equal to the precipitation rate once this is a saturated solution. So it's got to be saturated. If it's unsaturated, then more will dissolve. If it's supersaturated, then more will precipitate. And so this has to be a saturated solution. And so this is the equilibrium describing that, and that's given by KSP. Here. KSP is, of course, the activities. Activities would be more accurate than the stoichiometric concentration. Make sure I'm recording this. Yeah. So, you know, we take the activities. As long as the concentrations are not too high, then we'll just use the stoichiometric concentrations here. C naught is some reference concentration. So the one activity of calcium sulfate is 1. Got that. See, this reference concentration, C naught, is 1 molar. The quantity multiplying 1 over C naught is called the solubility product constant. And so this is the KSP here. This is 1. This is 1 if it's an ideal solution, it's 1. If it's not ideal, then it's not going to be 1. It's going to be a little different to compensate for the deviations from ideal behavior. But we're just going to take it as ideal. There's the activity coefficient that gets inserted in there. And these, you know, they're either given. Actually, we can find a table of KSPs. They're either given or you can determine them. We have a lab that we can do that determines the KSP value of these. So we analyze for sulfate, what's the sulfate content in there. But in that type of analysis, we do quantitative analysis. You guys have done quantitative analysis before, you know. For example, you analyzed how much sulfate was in a solid, but we could analyze how much sulfate's in a solution. How would we do that? We do that by separating out the solution. If we start precipitating out the sulfate, then we're going to have a Le Chatelier's shift here. So let's say we find it less soluble, or remove the sulfate. When we start removing the sulfate, then more sulfate will form, you know, by dissolution. This is precipitation first. And so KSP is the equilibrium. So there's no change. This is a dynamic equilibrium. In a dynamic equilibrium, the saturated solution is going to maintain the concentration. The saturated solution, this is what we call the solubility. The units, though, are typically different. You know, this is what we call the molar solubility. However, in most places, they don't give us the molar solubility. If we take a look at Wikipedia, let's go to calcium sulfate. In Wikipedia, I think this is going to take me to Wikipedia, yes. Like that. When we look at the data, the solubility is not typically written as molar solubilities. It's more commonly this. The reason it's this is it's a lot easier to measure. You know, you take 100 milliliters, how much will dissolve? 0.26 grams will dissolve in 100 milliliters. That's a quarter gram. Well, a quarter gram, what do we call calcium sulfate? Is calcium sulfate soluble or insoluble if a quarter gram dissolves? Sulfates are all soluble except for silver, lead, mercury, silver, lead, mercury. Calcium, strontium, barium. Mitchell's got it down good. Calcium sulfate is considered insoluble. So what's the cutoff? The cutoff is not in grams. The cutoff is in molar solubility. I wrote it down once. Do you guys remember that number? That number is 0.1 molar. So if we can get more than 0.1 moles to dissolve, then we call it soluble. If we can't get 0.1 moles to dissolve, then we call it insoluble. Well, 0.1 moles of anhydrous calcium sulfate is going to weigh 13.6 grams. But that would be per liter. You know, per 100 milliliters would be 1/10 that, so it'd be 1.36 grams. So if we get more than 1.36 grams of calcium sulfate to dissolve, we call it soluble. Well, we are only getting 0.26. So this flips it, and this is black and white. It flips it into the insoluble category, but is it really? So insoluble. So the things that are close, you know, we call slightly soluble. And so this is very qualitative, and those are qualitative solubility things, which we talk about in chapter 14 in Chem 1A. But, you know, solubility, this is the molar solubility. This is the quantitative version. When we talk about solubility, quantitative, that's the max. The qualitative solubility, we have some designations. We call it S equals soluble. It's greater than 0.1 moles. I equals insoluble. That's about less than 0.1 moles. And then SS, which we call slightly soluble, which is around 0.1 mole per liter. In this chapter, we're looking at the quantitative, not the qualitative here. Solubility. So we're going to spend some time looking at how much. You know, I don't want to know if it's insoluble or soluble. I want to know how much. That's the difference here. Well, we could figure it out. And so this is what I do. I set up everything with ice table. Your book is going to skip the ice table for some of these. And so if I'm interested in calcium sulfate, I'll just write out the KSP equation. The KSP equation is always the solid and its saturated solution. It's always the dissolution reaction. We only need one of them because the other ones are reversed. So if I'm interested in precipitation, I'm looking at going reverse. If I'm interested in dissolution, I'm interested in going forward. And so we don't need two equations. We just need one or the other. So even if I'm looking at precipitation, let's say I want to know how much is going to precipitate, I'm still going to write the dissolution equation and then just go backwards. The reason is this, because you can do lots of variations, lots of tricks after you master the basics, but if you start mixing it up, and I see this on tests all the time, people get confused. And so you always write it the same way each time. If you always write it the same way each time, then once you're comfortable with that, then you can do all the tricks you want, because if you reverse this, you have to invert the K. And the problem is people reverse this, they don't invert the K. But this is the KSP. And the KSP is 9.1 times 10 to the minus 6 here. And so what we do is we do this. We reset everything to the left. If we reset everything to the left, then we have calcium sulfate in just plain pure water. So there's no ions in solution. That is, we just dump this calcium sulfate in water. And then what's going to happen is we're going to lose some of the calcium sulfate. And we're going to lose some, but we're not going to keep track of it, because as long as we have excess there. But we can keep track of it using the stoichiometry over here. So if I wanted to know how many grams dissolved, then I'll go back and figure this out, how many moles I lost. But since we're dealing with molarity and concentration in the ice table, I'm not going to worry about it here. So if I'm gaining plus X moles per liter, then I'm losing minus X calcium sulfate. I have to be losing calcium sulfate. And again, we do a secondary calculation to figure out how much calcium sulfate must be lost for this to gain that. And so we end up with X. But we don't like to use X here because we can be more descriptive. Our X is just a generic change. And so rather than doing X here, we get rid of X. We're not going to call it X anymore in this chapter. Instead, we're going to replace this using S. Now, S stands for the solubility, quantitative. This is the max. This is where S is equal to the molar solubility. So it turns out that KSP is just going to equal S times S. It's just going to give us S squared, because it's going to be the calcium concentration at equilibrium times the sulfate concentration at equilibrium. And those should be the same, because it's a 1-to-1 mole ratio. And therefore, S is just equal to the square root of KSP, which is going to be the square root of 9.1 times 10 to the minus 6, which is equal to, I didn't bring my calculator, and I lost my phone. I gotta find my phone. So I'll just do it in Excel. 9.1 times 10 to the minus, what is it, 6? Anyway, it's small. This is less than 0.1 molar, and therefore it's insoluble. How insoluble is it? Well, it isn't 100% insoluble. Some will dissolve, and so we just call it insoluble because how much will dissolve? About 3 millimoles per liter will dissolve. So technically it's not insoluble, So about 3 millimoles, I'll just move the decimal there, per liter will dissolve. But 3 millimoles is too little to consider soluble. There's a huge range of solubilities. So one of the important things is we could calculate the solubilities, or we could calculate the KSPs. And so let's use the Wikipedia data to see if we get the same number for the KSP. So I'm going to take a look at calcium sulfate. So the first thing is this solubility is in the wrong kind of units here. It's 0.26 grams per 100 milliliters. Unfortunately, we don't have the density of the solution, do we? We would need the density of the solution to figure it out. Since I don't have the density, do I have the density? I could make an assumption. I could assume that the density is close to water. So let's just go ahead and try that. 0.26 grams of the dihydrate. So this is just 0.26 grams of the dihydrate. This is called dye. And the molar mass is 1 mole weighs 172.172 grams. It's for the dihydrate. And then this is going to be per 100 milliliters of solution. Or water. I think it's 100 milliliters of water. We'll just make an assumption here. Actually, we aren't going to make any assumption. We'll just do that. The problem is we're going to assume that this is a solution. It could be water. They should tell us. Because what they could do is they could just take 100 milliliters of pure water and add 0.26 grams of the dihydrate. And that could potentially change the volume, you know, when you dump in a bunch of salt in there. And we're assuming that if they took 100 milliliters of pure water and they add the dihydrate, we're assuming the volume didn't change, so it's the solution volume. Convert that to liters. All right, what's the molarity that you calculate here? Somebody calculate that for me. Should run my calculator.
I got 0.015 mole.
Give me one more digit.
151.
151 molar. All right. Now, the KSP is going to equal the solubility squared. And so this is the molar solubility here. This is experimental. You know, there's footnote 1 here. Molar solubility. So let's go ahead and put that in here, 0.0151 squared. Can you square your answer, Mitchell, and tell me what you get?
0.000228.
If we look at this, wow, that's way off, huh? What was it? Supposed to be 9.1 times 10 to the minus 6. We're way the heck off, aren't we? Way the heck off. But we have a problem And the problem is this. For +2 and -2 ions, do you think the interionic attractions are strong or weak? +2, -2. In other words, are we going to be influenced by effective concentrations that are going to be quite a bit lower, would you say? Yeah. So here we're making the assumption that this is ideal, but this may be not so ideal. Huh. Probably not so ideal. This is one of the limitations of the KSP concept. As long as the concentrations are small, then that's going to minimize the interionic attractions here. Or it could be that, I should take a look at footnote 1. Where did this data come from? But I already know that +2 and -2 are going to have significant deviations from ideal behavior. This is 0.01 molar. 0.01 molar, and then we go back over here and we take a look at let's go back here and take a look at chapter 14. Close this here. We already see quite significant. This is a +2, -2, magnesium sulfate. We already see significant deviations here. Well, actually, what are they, roughly? So at a 0.001, this is molality. Do you know why they use molality sometimes instead of molarity? Visual Mintech uses molality. What's an advantage of molality over molarity? Can you name one advantage of molality over molarity? Molality is more of a pain. I can name a disadvantage. It's more of a pain to deal with because the definition of molality is what? This is the same issue I was dealing with just a minute ago with the 100 milliliters. Is that 100 milliliters pure water or is it solution? Actually, we're not sure. We're not sure because they didn't specify. It could be pure water or it might be solution. In molality, at least they specify it. What is it? It's moles per kilogram of pure water. Is that going to be the same as a kilogram or a liter of solution? No. And so why even bother with molality? There's one major advantage. Why didn't they do it in molarity in Wikipedia? Why do they do grams per 100 milliliters? Maybe that doesn't really help. Actually, they probably don't even care. Wikipedia. Well, can you think of one major advantage of molality over molarity?
Molality is more specific. So.
Molarity is specific too. And both are specific. I mean, it's moles per liter or moles per kilogram. Seems pretty specific.
Is it because molality is like pure water, whereas molarity could be solution or water?
Well, molarity is always solution, and so it wouldn't be pure water in molarity. But it's not the composition. It has to do with a physical property, not anything else. It's a physical property. It's probably one of the physical properties that you aren't that familiar with, maybe. Or maybe you are. For example, like the Concorde. When the Concorde, you remember that supersonic jet? There was a major crash of the Concorde. But the engineering that was involved in that was tremendous because what happens when that thing got hot? You know what happened when that thing got hot? Yeah, it's They're talking about reintroducing supersonic jets. It's Air France. It was really expensive, but it was very fast flight. But it's a physical property.
Does it have something to do with the kilograms versus milliliters?
Yes, it does. The same reason why on a mercury barometer, did you guys have to correct the mercury barometer? Did we correct the mercury barometer in Chem 1A?
I think so.
Okay. Do you know mercury barometers are calibrated at 0 degrees C? Why don't they just calibrate them at room temperature? And here it makes sense. You know, I usually complain a lot in Chem 1A that STP is such a waste of time. It's such a waste of time to memorize. But maybe it's not for some people, but I think it's kind of a waste of time to memorize because you don't work at standard temperature for gases. Standard temperature for gases is 0 degrees C. Right? But it makes sense for barometers because as the mercury heats up from freezing, it expands. And so when we do a barometer correction, it's always a subtraction. If we calibrated it at 25 degrees C, then if it's warmer than 25 degrees C, the correction is a subtraction. If it's colder than 25 degrees C, then the correction is an addition. So it's a hassle. And so they calibrated at 0, assuming that nobody's going to be working at 0 and everybody's going to be working above 0, and therefore everybody's going to use the same correction factor. And they have a table that they publish with the correction. But anyway, here, there's a crazy amount of gaps, you know, when you looked at the Concorde. The crazy amount of gaps in the airframe to account for expansion once the friction heated up the aircraft. In fact, it had so much room to expand, it leaked fuel constantly. It was up to speed and the plane sealed itself with expansion. So as metals heated up, they expanded. That's one major advantage of molality. Molality never changes with temperature. Molarity changes with temperature, because volumes tend to expand when they get hot. And so molarity is temperature dependent, molality is temperature independent, because moles don't change with temperature and kilograms don't change with temperature. But densities do change with temperature. I was working with acetone. And acetone, actually, you know, at UCSB, they have these old military barracks that they converted into labs, and the climate control is awful in there. So in the summertime, it's hot in there, and then it get cold, and then hot. You could literally see the acetone expand and contract, you know, in like a 3-hour lab period due to the temperature fluctuations in the lab. Anyway, so this, and that changed because I was extracting caffeine into, or the experiment called for extracting caffeine. I wasn't doing it because I was the teaching assistant there, but one of the students was doing it. And the molality was fluctuating, molarity was fluctuating radically. But going back to this, do you see the +2 and the -2, you know, already at 1 mole out is already 50% unclustered. I mean, it should be 2 here. 2 independent particles, but it's behaving as 1. It's heavily clustered. It's +2, -2. It's +1, -1. It's +2, -1. And so, you know, just some frame of reference, but let's see what the concentration of ours was. Concentration of ours was 0.01, almost 0.02. So between 0.01 and 0.02. We go back to this, looking at magnesium sulfate at 0.01, you know, there's already significant, maybe 25% clustering here. So let's take a look at how far off. We're off more than 25%. You know, we're off by 2 orders of magnitude here. And so there could be other factors here. And so this was experimental KSP using this. I don't know what the source of this is. I probably should look that up, but I'm not going to waste too much more time. This is how we do it. You know. The next way we could get the KSP is by using Appendix D data and Chapter 13. We could do it this way. In fact, there's a homework problem from Chapter 13. I don't know if you recall. This is why I'd like to do Chapter 13 after doing all this. It's way better, in my opinion. And so Chapter 13 used to be Chapter 18, which I preferred greatly. But anyway, we can figure out what the KSP is. You know, the KSP for this equation is, do you recall the K equation? Delta G is equal to, this is for non-standard conditions, delta G non,
Plus T delta S.
RT ln
Oh, right.
Q. Delta G non. If we're at equilibrium, then Q goes to K. Delta G naught is equal to RT ln of K, and K is equal to E to the minus delta G naught over RT. So if we figure out what delta G naught is, then we could get this. Delta G naught's very easy. What's the easiest way to get delta G naught? This is going to be at 298 Kelvin. Well, that's fine. We want the solubility at 298 Kelvin, or K, 298 Kelvin. What's the easiest way to get delta G from Appendix D data?
H minus T delta S.
Probably not that way. I would say the easiest way is just to take the sum of the delta G's of formation for the products minus the sum of the delta G's of formation for the reactant. Probably say that's, the product here would be the delta G of formation for calcium ion. We have 1 mole. This is delta G of formation, 1 mole sulfate ion, minus the reactant. That would be the delta G of formation of calcium sulfate solid. Now, if we have the data, that would be great, and we can calculate it. And so let's see if the data is available. Calcium for sure, sulfate for sure, but calcium sulfate, I'm not sure if we have that data. So let's go to Appendix D and see if we have that data, which would be probably A20. No, A19. Okay, are we? Yeah, we're in luck. We have delta G, calcium sulfate. So we have the delta H. Can I get this thing? Here's our delta G of formation, minus 1322. And then calcium is minus 542.8 here. And then we'll have to look for sulfate. And so minus 542. Oh no, I'm in the wrong column. Minus 553.6. kilojoules. And this on the end was a minus 1322. So let's find sulfate. Shouldn't be a problem to find. So it's going to be S. So I'm going to guess it's maybe 22. No. 23. Sulfate is minus 744.5. So we take our products minus the reactants. So can somebody calculate this?
I got 23.9.
23.9? Okay, thanks. All right, so let's go ahead and calculate our K. This is going to be at 298. It's going to be E to the minus 23. I'm going to convert this to joules. 23,900 joules divided by R, which is 8.3145 joules per Kelvin. This is all per mole, so I cancel out the moles, times T, which is be 298 Kelvin. So what do we end up with here?
I got 0.9904.
0.9904? Wow. And then 0.9 times 10 minus 1. Can you take this square root of this?
The square root, I got 0.9951, or 0.9952.
We don't want to round it. Just leave it there. You don't need that many digits. Wow. Uh-huh.
For K, I'm getting 6.46 times 10 to the negative 5.
For K,
Yeah.
6.46 times 10 to the negative 5.
Oh, I forgot to convert to joules.
Okay. Let's try that again then. And then this is going to give you solubility of what? Molar solubility. So just take the square root of the KSP.
I got 8.04 times 10 to the negative 3.
All right, so let's compare the KSP from both 9.1 times 10 to the minus 6. It's 6.5 times 10 to the minus 5, so it's off a bit. And the solubility, 0.08 versus 0.01, so it's off. Actually, no, the solubility, what was the solubility we calculated here? Based on their KSP given in the book.
We got 0.00302.
So 302 versus 804. So it's a bit off. Well, those are some calculations that we did. So we'd have to sort through those calculations. This is why, this is why the discussion section in scientific reports is the longest. And this is a very common headache in science. If you do science, you have these types of situations. Why don't they match? They should all match. Well, let's take a look at this here. We're gonna jump to 18.4 right now. We'll talk a bit about that. They say that the hard part of science is not doing the calculations. I mean, for example, ideal gas law calculation, how old do you think a child has to be in order to be able to use their calculator to do an ideal gas law calculation? They don't have to understand it, they just have to punch the numbers in. Probably like 5 maybe or something, So doing an ideal gas law calculation isn't anything special. You could have a computer do it, right? The hard part is knowing the limitations of ideal gas. What is an ideal gas? What's a real gas? Why do real gases deviate? How reliable or how much confidence can you have in an ideal gas calculation? That's the hard part. And so there's a very, very famous quote from one of the early scientists. I have it written down, but I forgot. But it says it's not so much what the numbers are, it's what the numbers mean. That's the hard part of science. And so it doesn't matter, nobody's really going to care if you can do an ideal gas law calculation. Everybody's going to care if you understand what the numbers, or how to interpret the numbers. And that's what we have in discussion. And so we need to know limitations. This is why I spent so much time talking about activities and that kind of stuff. We have repeatedly used the term slightly soluble in describing solutes, etc. You might wonder if we can write KSP for expressions of moderate and high solubility. So sodium chloride, is that infinitely soluble? No. Let's say I want to make some salt water. You know how many grams of salt you can put in water? We could look it up, but I have it memorized because I've seen it, if you see a number over and over again. But it's like 36 grams. I don't have it precisely memorized, but about 36 grams of salt. I need to know how much sugar I can dissolve in water because that would probably be more useful, because I don't want that much salt. But anyway, sugar, how many sugar cubes can you dissolve in a cup? Have you ever tried that? Yeah, it's not that many. And so, but we call those soluble. Sugar is highly soluble, salt is highly soluble. Can we use KSP to calculate this? No, that would be kind of a worthless calculation. You know why? Because in ionic solutions of moderate to high concentrations, activities and concentrations are generally far from equal. And so this is, of course, maybe, if we wanted to do this, maybe not in this class, but maybe in the next level class you could do it, because if you use activities instead. And what we're going to do is we're going to use activities. We're going to use activities. Well, actually, we're just going to have there's a database of activities that, what was that program called? There's a database of activities at this program, the one we tried yesterday. Visual Mintech. Yeah, the Visual Mintech maintains a database, and they update it every year of activities. You can read about it. And they try to keep that like the latest. For example, in point 1, so here they're giving us some kind of reference, how big was the mountain you climbed yesterday? oh, it's huge, really huge. It's like 200 feet or something like that. So different perspectives. So we need some numbers. We have to be quantitative. It's not like you have to know the elevation of every single mountain in the U.S. No, you don't have to do that. But you should know like the biggest. You know what the biggest one is? Hmm? Yeah, Denali. Yeah. How about in the continuous U.S.? Do you know the biggest? Well, it doesn't matter, but if you're somebody who likes to climb mountains, you probably would want to know that, right? And you want to know how high it is, Just like if you're a chemist, you want to know, some numbers. Not every single mountain in the U.S. is ridiculous, but you'd want to know a few numbers. And we're already thinking about percentages, so we already know certain percentages, like magnesium sulfate was already 50% ion paired at 1 molal. That number I would think is pretty significant. And so if we look at 0.1, okay, this is molar, it's not molal, but molar and molality aren't going to deviate that much. The reason they aren't going to deviate that much is because a kilogram of solution is going to be about a liter, nonetheless. And, but, the volume is going to change when you dump in all that salt, It might change a little bit. So it's not going to be exact, but if we compare this, like we compare 0.1 molar, KCl is not going to deviate so much because it's a +1 -1, right? But even at 0.1 molal, this is 24%. So the activity, it's already down 24%. So if it was supposed to be 2, it's going to be at 1.5. And so that's already pretty significant deviation. If we cannot use molarities in place of activities, much of the simplicity of the solubility product concept is lost. So this is why we have things like visual min-text, so we don't have to, And so these calculations are pretty meaningless. It's like if somebody asked you to do an ideal gas law calculation at, 1 million atmospheres, it'd be kind of stupid to do. It's going to be so far off. Probably at 1 million atmospheres, the gas is already liquefied. Or, there are other things. And so we limit these KSP calculations to slightly soluble, essentially insoluble solutes, and ion molarities are used in place of activities. So, of course, the calculations are going to be better, the lower the solubility is. So if the solubility were like 10 to the -6 molar, versus 10 to the -3 molar, then 10 to the -6 molar is going to be more accurate. 10 to the -9 molar is more accurate. When you get to 10 to the -1 molar solubility, it's probably not going to be so accurate. But that's all right, because we do the same thing with ideal gas law. The ideal gas law is so easy compared to the Van der Waals equation that we tend to use that and then know when it's going to be good. For helium, ideal gas law works wonderful. Ideal gas law for helium should work, almost down to 4 Kelvin. Helium liquefies at 4 Kelvin. But for steam, it's not going to work so well. There's other things, and this becomes related to activity as well. And this is the diverse non-common ion effect. Not only can ions pair, we're looking at calcium and sulfate and magnesium and sulfate. They're going to form ion pairs and clusters. But what if you dump in some unrelated salt, like sodium chloride? And you think, sodium chloride, that's not related to magnesium or calcium sulfate in any way. But what happens is the sodium ions can cluster around the sulfates and the chloride ions can cluster around the magnesium or the calcium. This is called the salt effect. And so the activities become smaller when you add an uncommon salt, a non-common salt. And so we have the common ion effect. This is called the uncommon ion effect, or the non-common ion effect. What happens is solubility actually increases. It increases because it reduces the free ion concentration. So this is like a Le Chatelier shift, but it's a really weird one. And so, let's see, there's a figure here that we should take a look at. For this. let's see the figure. There's no figure for this, unfortunately. The Brave doesn't have a good. Well, they need. I would like a figure for this, but it's the same thing. It looks exactly the same as the common ion effect, except the only difference is rather than clustering with the same, it clusters with different. So it's a big party. They have the ions, and so it doesn't matter. We know electrostatic interactions. Negative is attracted to positive. It doesn't matter what the positive is, any positive. And the higher the charge on the positive, the better. So even if you have plus ones, of course the plus twos are going to get in there, but if you had plus one sodium ions, we'd form clusters there. Well, forming clusters of the sodium ions is going to decrease the free fluoride here. Or if we have chloride ions, the chloride ions would cluster around the magnesium and reduce the concentration of free magnesium. When we look at these in the KSP equation, when we look at that equation, it's the free ion that's in there. Okay, this is different though. This is an ion pair. This is the reason why HF is a weak acid. The weak acid HF is because of ion pairing. Fluoride's very small in charge. Oxide has a bigger charge, but oxide's not stable in water. So incomplete dissociation. So what we form is, this is not like magnesium fluoride solid. This is just an ion pair that, and it's hard to break up. And so this is called the MgF plus ion pair, and it's not ionically bonded. It's just a positive negative attraction. This can break up, and so if there's a big collision, it can break this apart easily, but they tend to reform. And so we have ion pairs that form from incomplete dissociation, like MgF plus. And so MgF2, let's say, thus, although the measured solubility of MgF2 is about 4 times 10 to the minus 3 molar, that's the measured solubility, we cannot safely assume that magnesium 2 plus is 4 times 10 to the minus 3 molar in fluoride. Actually, the solubility is much higher. The solubility is much higher because of these ion pairs that occur. This means that the additional solute must be present for the product of ion combinations to equal the KSP of the solute, making the true solubility of the solute greater than otherwise expected. Yeah, the solubility has to be greater because we need not only to get free magnesium, we have to form those pairs as well. And when we look at the total solubility, we have to count the total concentration of magnesium in all species in solution. And so we have to look for these weird species here. The degree of ion pair formation increases as mutual electrostatic attraction of the anion and cation increases. Hence, ion pair formation is increasingly likely when the cations or anions in solution carry multiple charges. For example, magnesium sulfate, yes, which we already talked about. The final thing for limitations is simultaneous equilibria. When we factor all these things in, ion pairs, not only that, we also have complex formation as well, which we haven't talked about here, but we'll talk about it now. Complex formation can also be, and complex formation is kind of like ion pair formation. So here, you know, when we have PBI2, what we expect for PBI2 is this. This is the ideal, you know. PBI2 ideally breaks into 1 Pb2 plus ion and 2 iodide ions, right? But we already saw in chapter 14 that's not the case. This is why you want to make these connections, and this is why you want to go back and take a look at things. So we're on page 838. You've seen PBI2 before, right? Do you recall it? Or PBCl2? One or the other. And that was here. And so we try to make connections. And the more times you see it, the easier it is to make these connections. Oh, it wasn't either of those. It was PBNO3. NO3 2. Lead 2 nitrate, this is pretty soluble here. But look at the deviation. This should be 3. It's 131. It's significant. So we see significant ion pairing or clusters, or what did we call these? What did we call those? Interionic attractions in aqueous solutions. The positive is surrounded by a shell of negative ions. So we'll call this a cluster. They just call it a shell. So clustering might be. Now what are the identities of the clusters? We can identify. Some of them are like this, you know, except these would be +2 with -1s. But these are the types of species that we're going to find in addition to the clusters. Do you see any clusters here? No, there are no clusters here, but the clusters are going to screw up the concentration, the effective concentrations. We're going to have the activities. So it's actually, the picture is more complex than this, but how do you quantitate the clusters? That would be more of a difficult situation. And so the black is ideal. But we already know we have ion pairs, so this is incomplete dissociation. So one iodide gets stuck on. It's not ionically bonded, but it's forming a pair like this. So rather than splitting up into 3 particles, it splits up into 2. The other type of ion pair is, okay, the PB breaks off and 2 iodides break off, but the 2 iodides link up. Now PbI2 is like a molecule versus PbI2 solid is a lattice. And so we have these molecular units here. They're not going to have any charge, but it would be a cluster. And these clusters are much more strongly bound. We call them ion pairs, which differentiates them from the shells that were formed in chapter 14. And so this would be like a little molecular unit here. So far, the amount of free, we call this free lead ion, is only a small part of it. The solubility has to be much greater. And in fact, if we were to quantitatively determine how much free lead in there is, and then relate that back to how much dissolved, that's wrong, because there's going to be clusters and molecular units like this. So what we have to do is we have to figure out what is the number of moles of these, what's the number of moles of this, and what's the number of moles of that, and that's the total moles of lead dissolved. But then it gets even more screwed up, because PbI2 can also form if you add excess iodide. If we add excess iodide, we can form this triiodido plumbate 2 ion. The triiodido plumbate 2 ion, this is actually quite common here. And this PbI2, which is a yellow precipitate, can dissolve if you add too much iodide. And so if you're trying to precipitate this out and add too much iodide, it dissolves and forms these. We don't call these ion pairs. We don't call these clusters or shells. You know what we call that? We call this a complex ion. And we name it differently too. This is more of an ion pair. That's not a coordinate covalent bond that holds these together, right? This is just a positive negative attraction. Whereas over here, this is a coordinate covalent bond, because that's an actual complex. And so we have 3 iodides covalently bonded with lead. And then if there's even more iodide, we get the tetraiodido plumbate 2 ion here. So when we look at how much PB dissolves, PbI2 dissolves quite a lot, because we have to form all this stuff. It's still insoluble, so quite a lot is just relative, you know. But what do we do in a situation like this? Do you want to do 1, 2, 3, 4, 5, 6 simultaneous equilibria? No, that would be horrendous, right? But for this, in fact, we're going to do this. We're going to do this one, but we're going to use Visual Mintech to do this one. And Visual Mintech is more than capable of handling this. And so we could easily figure out the solubility of PbI2. But if we wanted to know the solubility of PbI2, it would be a bit of a challenge, you know, using K. And Visual Mintech also maintains a database of KSPs as well. KSPs, KAs, KFs, everything. And so a lot of work went into Visual Mintech, and this is why I think places like NASA might use it. Assessing the limitations of KSP. Let's assess the importance of the effects of the discussed section and some of which apply to calcium sulfate. So we just did calcium sulfate, a bunch of calculations for calcium sulfate. Recall that in example 18.2, we calculated KSP for calcium sulfate on the basis of its measured solubility. So yeah, we did. Our result was a KSP, actually 18.2, I didn't do 18.2, did I? What was I used Wikipedia. And what did we get when I used Wikipedia data? They used probably some other data. Let's see, with Wikipedia.
1.2 times 10 to the negative 4.
Oh, okay. Well, that's what we got. So they probably had the same data we had. I just got it off Wikipedia. And so they use the same. So they got we got 2.28, they got 2.3. So I assume they're using the same. And I guess Wikipedia, that kind of data, I think they actually take from like the CRC. The CRC has a ton of paid people that keep track of this stuff year to year to make sure it's reliable. But anyway, our KSP was the same, 2.3 times 10 to the minus 4. This value is about 25 times larger than the value listed in table 18.1, which is a KSP of 9.1 times 10 to the minus 6. So when you see this 25 times difference, it doesn't really give you a whole lot of confidence because 25 times is like 2,500% error, something like that, right? And so it's not like, wow, you know, we're off by 2 powers of 10. These conflicting results for calcium sulfate are understandable. The KSP value listed in table 18.1 is based on ion activities, whereas the KSP value calculated from the experimentally determined solubility is based on ion concentrations, assuming complete dissociation of the solute into ions and no ion pair formation. So the KSP calculated from experimentally determined solubility is based on ideal, you know, ion concentrations. So it would be like this black here, ignoring all the blue. Well, that's because of solubility. I don't know. That seems wrong to me because solubility is, if it's experimentally measured, should just measure how many grams of this dissolves, regardless of what species it forms. But I'm not going to worry about it too much right now. We just want the take-home message. What's the take-home message for this? And this is usually what I annotate in the book. I told you many times I annotate stuff. I don't like reading the book anymore. When I first started, I read the book and then I reviewed. I like studying from notes myself. And so I take notes because the book would take too long to read, but we're reading it right now because this is very short. There's only 1 paragraph. Like the activity thing was 2 paragraphs. But this is 2 paragraphs, so this is pretty short. So we're going to read the whole thing. I usually tell people just to read it. Usually, but it's not. This is difficult to read, I'm sure. The KSP value in table 18.1 is based on activities, whereas the KSP value calculated, so can I remember that? That's kind of hard to remember. But in KSP, so we have a table of KSPs. All those KSP values should be pretty accurate because those are based on activities. Whereas the KSP value that we calculated experimentally should be off. So what this is telling us, the take-home message here is that the KSP values in table 18.1 are reliable, but if we're using the KSP values to calculate the solubilities, then are we going to get accurate solubilities? Well, anyway, we'll continue to substitute molarities for activities of ions. And you're thinking, why? Because it's giving us 25 times error. In the case of calcium sulfate, simply suggests that some of our results, although of the appropriate general magnitude, that is within a factor of 10 or 100, may not be highly accurate. These order of magnitude results, however, still allow us to make some correct predictions and to apply KSP concept in useful ways. So what we do is, this is very common in science. Like, is the oxidation state 100% accurate? You know, when I calculate oxidation states, is that 100% accurate? No, it's not. You know, is the charge on carbon in methane really -4? No, it's not. Are there ionic bonds between the carbon atoms and methane and hydrogen, which is +1? No. But they're very useful because even though they might not be 100% accurate, we can make accurate comparisons. So if we compare methane with CO2, then even though those numbers might not be accurate, you know, we can see we're going from -4 to +4, and that type of information is very, very useful. And so even though these calculations, you have to be careful with these calculations in how you analyze them. This is the difficulty in science. They're still useful because we can make accurate comparisons. So if we compare calcium sulfate to magnesium sulfate, yeah, that's great. You know, magnesium is soluble, calcium is insoluble, strontium insoluble. And so we can make those types of comparisons quite easily. And so even though, and this is the same thing with the ideal gas law, except the ideal gas law, they didn't go into it as quantitatively as they probably should have. And then we should have, I usually in Chem 1A, but most people probably forget this, but they do the same calculation using the ideal gas law and the van der Waals equation and see what the percent difference is, van der Waals being more accurate. All right, so we did calcium sulfate, but now we're going to ignore all this stuff and then just use this, because what we're going to do is we're going to do the comparison. So I'm not going to worry about this too much, and I'm not going to worry about doing activities until we do visual MinTech, you know. And we're going to calculate the solubility of PBI2 and then compare it to the solubility that we generate from visual MinTech and see what the percent error is. Visual MinTech would be very accurate in terms of determining, what I want to know is how many grams of this will dissolve, or how many moles of this will dissolve in a liter of solution, you know. And so this is why I've divided visual MinTech into two parts. One part being this, the second part being acids. All right, so let's go back to the table here. There's a better table in the appendix of KSP, so let's take a look at that table here. Let's see. So we have the Ka table in the appendix, the Kb table for the means. And so Ka, Kb, and then what's next? The next table we encounter in appendix D is the KSP table. So we just saw calcium sulfate. So the first thing what we do when we have a new table is, okay, calcium sulfate was 9.1 times 10 - 6. The first thing we do is, we take a look at the range. What's the range of KSPs that you see? So we look for the biggest and the smallest one. So the smallest will start there, -33, -31, -29, 31, 44. -44 is the smallest so far. 46, 51, 53, so I see it looks like 2 times 10 - 53 is it. That's the smallest KSP. So that should have the smallest solubility, but the solubility is very tricky, because is the solubility always the square root of the KSP? No. The solubility depends on how it splits up. So for example, if it splits up into 2 ions, then yes, it is a square root. But if it splits up into 3 ions, no, it's not. If it splits up into 3, it's equal to 4 times the something something. And so we'll have to figure those out. But what is it? 10 - 53. This is mercury 2 sulfide. And do you see that little footnote B? What is that little footnote B? You see, I see a B over here, and then there's another B here. And so what do all the B's have in common? Footnote B. Here's another B. Do you see what all the B's have in common? Here's another B. Not only that, when I look at the B's, all the B's are small. 25. Pretty small. 37 is pretty small. They're all sulfides. So B's are all sulfides. And then there's a footnote A here. And so we need to know what the footnotes state. Where are they, A and B? C, D, all right. These are KFs. The KFs are the second half of this chapter. C, D, where the heck? So if they had it right there, it'd be a lot easier, but they don't. Where do they have the footnotes? So we're on 27, let's go to 33. Maybe that's going to be where. I think I might have gone too far, or maybe I need to go all the way at the end. 38, let's see. No, I went too far. Maybe it's an end note, so that's why I'm going to try to go to the end here. During an exam, I gave this table out on one exam, and a student came up to me and asked me, what is B during the test? But I couldn't tell them. This is part of the test. It's part of the test because B does something very special. And I don't know. I'm going to dig around. I'm not going to dig around anymore. But you should look it up because it's important. And so let me tell you what B is. The reason I didn't tell them is they should have known this. What do you know about the strong bases?
They hydrolyze completely.
Yes. And so this is what we have. This is the footnote B. So this is the one that wins the award for having the smallest KSP. And KSP is going to be the equilibrium between the solid and its saturated solution. So its saturated solution, this should break up into ions. We're going to just do ideal. Everything's going to be ideal here, but in this case, I'd expect some ion pairing, I'd expect clusters, I expect all this other stuff to be happening, but we're going to completely ignore it because that's going to be too hard for us to solve. And we're just doing this for cross-to-cross comparisons. Correct? And so this should break up into Hd2 plus and S2 minus. But the situation is this is not KSP. This is not KSP. And the reason it's not KSP is because does sulfide exist in water? Sulfide doesn't exist in water. What's going to happen with sulfide is sulfide attacks water. It's too strong in base, and it's going to produce what? HS minus and OH minus. K for this is very, very large. Or not very, very, it's very large. K for this is very large. This is KB, by the way. So this one's more complicated. So we add these two equations up, the sulfides cancel, and we end up with HGS solid plus H2O liquid. This is going to go to Hg2 plus HS minus plus OH minus. And this is KSPB. I usually call it KSP double dagger. Or just KSP. And so for all the sulfides, sulfide's too strong of a base to exist in water.
Does that mean we can't use those KSP?
No, this is the KSP equation. in other words, for sulfides, this is not the KSP equation, not KSP equation here. This is wrong equation. And so what was that value? That was times 10 to the minus 50. What was it? Let's take a look at that value here. Okay, no, that was 26, I think. Mercury 2 sulfide 2 times 10 to the minus 53. This is the 2 times 10 to the minus 53. This is not. This is not equal to 2 times 10 to the minus 53 here. This is the wrong equation because this equation just doesn't happen. So there's no number for this equation because sulfide's too strong of a base. Does that make sense? So for all of them, we have to do this. For all of them, we have to add water. Because the water will be attacked. And so, unfortunately, the student who came up to and asked me didn't know about the sulfides. And so here, this is going to be FeS plus water yields Fe2 plus HS minus plus OH minus. That's the KSP because it's a B. Where else? There's sulfide. Here, it's the exact same equation. PBS solid goes to PB2 plus HS minus plus water plus HS minus. Yields PB2 plus HS minus plus OH minus. This is the KSP for that. If there are two sulfides, it's going to screw everything up, but I think we're going to get lucky here, except for silver. Silver is going to be a little bit screwed up because we have two silver ions. And so this is going to be Ag2S solid goes to, or plus water goes to 2Ag plus. It's not that screwed up, but the pattern's a little bit different. Just for silver, but all the others have the same pattern because they're 1-to-1. So tin, zinc, and all these others are going to have the exact same pattern as what we just did for mercury 2, and the only different one would be silver. But that's fine. Now the KSP splitting pattern is different too. So for example, this one's more complex, zinc phosphate. This is going to split up into 3 zincs and 2 phosphates. So the solubility in the KSP are going to be more complex. We set up the ice table for this. We'll do this next time because we're out of time today. But hopefully you're comfortable with activities now that, this may